Good afternoon, everyone, and thank you for joining on behalf of Planetarium, Prime Minister's Museum and Library. I'm delighted to welcome you all to today's exciting webinar on space weather, understanding the sun's impact on Earth. This event is organized as a part of World Space Week 2024, a global celebration of space, science, and technology. Our speaker for today is Ms. Megha Rajoria, an accomplished astronomy expert, science communicator, and active scholar. Ms. Rajoria has a long history of collaborating with Nehru Planetarium, having worked on various projects and workshops over the years. Since 2008, she has been working under the guidance of late Dr. N. Ratnashri on the restoration of Jantar Mantar Observatory instrument in Delhi. Her dedication to preserving and raising the awareness about Indian rich scientific heritage has been a driving force behind her work. Ms. Rajoria is also a trained citizen scientist and astronomer who actively engaged in high resolution analysis of night sky through image captured by GMRT at NCRA campus in Pune. She was previously part of RAD at Home India, the first Indian citizen science research program in astronomy, demonstrating her commitment in involving the public in scientific discoveries. In addition to her extensive work in astronomy, Ms. Rajoria has collaborated with organizations like Doordarshan and the Council of Scientific and Industrial Research, National Institute of Science, Communication and Policy Research. Currently, she is like actively involved in promoting astronomy education through digital lectures and workshop, while also volunteering for Tactile Astronomy initiative with the Blind Relief Association schools in Delhi. Recently, Ms. Rajoria monitored undergraduate students in the Jantar Mantar Positional Astronomy project with Nehru Planetarium, where she trained them to take accurate reading at the historical observation in Delhi. She's even presented her research paper on this project at IAU Symposium in Ethiopia. Now, presently, she is actively involved in astronomy outreach education in USA by giving public lecture and involving people in public night sky observation. We are truly fortunate to have such a knowledgeable and passionate speaker today with us who will guide us through the complexities of space weather and sun's impact on Earth. So we'll take a setback and we all are eagerly waiting for Mr. Joria to share her presentation related to the subject. Over to you, Megha, and warm welcome from Nehru Planetarium.
Good evening, everyone. Thank you, Prerna ma'am. Am I audible and visible?
Yes, you're audible.
Okay. Thank you for inviting me today. And as ma'am pointed out, that we are celebrating the International Week of Space uh, from 4th to 10th October. And the theme for this time is climate change, space and climate change. And in lieu of that, this time we thought that let's talk about something that curtails space weather. So we will talk in detail about space weather today. Let me share my screen. Okay, is my screen visible?
Yes, Megha.
Okay. So before we talk about space weather, let's first understand very basic definition of what weather and climate is. So a lot of times I've come across a lot of people I know, in fact myself, while we were in school, that what is weather or climate? What's the difference? So if we go to very basic level, if you can recall when you watch news in TV, they say today's weather report. So something which is very short term, that something the weather condition, the atmospheric conditions that are short term, that includes today's or tomorrow's, or let's say a week or two's atmospheric condition, that is weather. So like a couple of days or a week or two. So temperature, humidity, precipitation, everything, that's weather. But when we talk about climate, climate is something that is over a period of decades, like 2, 3, 4 decades, like 30 years. For example, Prerna ma'am is in Delhi right now. So Delhi has extreme type of climate where you have extreme cold, extreme summer, extreme monsoon. So that's the difference between weather and climate. So with this basic understanding what weather and climate is, Let's move on to space weather. So, what is space weather? Space weather is more like the conditions, the environmental conditions that are in the space out there. And because our stars, the dynamic sun, causes most of the activities in our solar system. There are so many solar activities that are going on, which comprises our space weather. So there are a few phenomenons, that are the major reasons or the causes of these environmental conditions, which is what space weather is. Now, these phenomenons are solar flares, coronal mass ejections, solar winds, and geometric storms. Now, why are we studying space weather, or why there is so much interest in space weather? Although space weather was, I think, if I can recall correctly, around 1800s, it was this term came up, and we started looking there about what space weather is and how to monitor it, etc. But today, when we have so much space technology, especially satellites, our whole communication system, the grids on the ground, everything is so very well connected with the satellite communication up there. It's very, very important for us to monitor space weather, because the solar activity that is going on in the space, if it harms or it has any sort of effect on the satellites or communication system, it's eventually going to affect us, because globally we are so connected. So we will talk in detail that the examples of how or when in the past that happened, or what are we doing about it, etc. So, before we move on to further discussion, let us first understand some basic terms. So, starting with the first phenomenon, which is solar flare. So, you can see in this GIF, and I'm sure if you have ever seen sun through a solar telescope or seen a picture, there are like tons of picture where there's a small like flare, like a small line in the picture, and then usually the astrophotographers and the astronomers, they point it out, oh, this is a solar flare picture. So that's what a solar flare is. It's nothing, it's basically a sudden burst of radiation, and it releases a lot of energy across the electromagnetic spectrum, and it lasts for 20 minutes to 3 hours. So it's not like a very long term flare. It's like lasts only for a few hours. And also, so what's happening is there are magnetic field lines near the sunspots, and I'm sure most of you must have seen sunspots. There are those cold spots and cold regions in the sun that comes really beautifully on a sun picture. You can see those dark patches on the sun. So what happens? These sudden explosions of energy are solar flares, and these solar flares sometimes they become very intense. The radiation that they release, that can interfere with the radio communications here on Earth, and we will further see how that happens. So the next phenomenon is coronal mass ejection. So coronal mass ejection is more like there is a mass which the sun is ejecting, if in very basic terms we understand. So there's a large expulsion of plasma and magnetic fields from the sun's corona, the outer layer of the sun. Now, this travels towards the sun, and it takes a couple of days sometimes, but again, it interacts with the magnetosphere or the magnetic field lines of the earth, and it can interact with that. It will interact with that, as well as it may interact with the satellites that are coming in between. And sometimes when these coronal mass ejections reach the surface of the earth, sometimes the geomagnetic storms are so intense that when they reach the surface of the earth, they can even cause harm to the power grids. So we will not go into too much detail of that, but we will see that how that happens, and what implications it has over our systems here on the ground. So the next phenomenon is solar wind. So a solar wind is nothing but a continuous stream of charged particles. So there's a continuous stream of charged particles that the sun, is giving out, it is releasing, and then they come and interact with the Earth's magnetic field. All right. So far we have understood that what these basic terms are. I had one more term, but let me see. Okay, yes. So another important term is geomagnetic storm. So right now, if you guys are following any pages of astronomy, you must be seeing some really beautiful pictures of auroras that are coming up these days. And this is one of the picture I got from internet. And geomagnetic storms are disturbances in the magnetosphere. Again, when solar wind or coronal mass ejection is continuously coming and at a very intense rate, it causes a sort of a storm, a geomagnetic storm. And that leads to auroras and may lead to disruption in technology as well. So, for example, right now it's a G4 storm, which is considered to be a very high rate, intense storm, which is going on right now based on our solar cycle and everything. But we will see some more graphics of that. So let's go back to the part where we understand how these particles are coming towards the Earth. And so, if we look at these particles, they are perpendicularly coming towards the Earth. So if I use a simple, a simple Fleming's right hand thumb rule, and you can see that the particles are coming towards the Earth, and these particles are interacting with the magnetic field of the Earth, which is my index finger. So when it is interacting with the magnetic field of the Earth, they are sort of going like this. Why? Because our magnetosphere, our magnetic field is trying to protect. The Earth's magnetic field is protecting us from these charged particles that are coming like this. So they are coming like this, but because of the magnetic field, they are going on the sides. So when they are going on the sides, what we see here is, if you follow the right hand thumb rule and you see that my thumb is pointing towards the poles, and you see the loop here at the North Pole and the South Pole. So you can reverse it as per the conventions. And because when the positive particles are coming, the direction will be like this, and when the negative are coming, it will be inverted. And not just that, so when these particles are coming, they are, of course, since they're charged particles, they enter the magnetic field, they try to enter, some of them get deflected, some of them accelerate and enter the Earth's atmosphere. So when they enter the Earth's atmosphere, they enter from the North and the South Pole. And this entrance point is where the aurora happens. So most of the time, or I mean, actually, the aurora happens at the North and the South Pole. And why is that happening? Because if we see one more, okay, let's look at this one. We'll go back to the previous slide. If we look at this slide, you see the Earth here, and we see that the photons, charged particles, are continuously coming, and some of them are deflected, but a few of them are not deflected. Few of them are entering the Earth's atmosphere, and they interact with the gases that are already there in the atmosphere, oxygen and nitrogen, and that's how those colors are produced. So auroras are caused by interaction of sun's plasma and Earth's magnetic field. So these two things are the reason why you see such beautiful scenic views of the auroras. So the sun releases charged particles into space through solar flares and coronal mass ejection. That's what we have understood so far. And Earth's magnetic field is acting like a barrier, a shield, and it is deflecting most of the particles coming its way. Like you can see in this picture, that you can see the direction how these particles are going, not perpendicular, they have basically deflected like this. And some of these particles are captured, and they basically enter the Earth's atmosphere from the top and the bottom, that is the North and the South Pole, and they collide with gases like oxygen and nitrogen in the upper atmosphere. So if we look at this particular picture, this graphic, you can see that it's the same phenomenon, that there is a coronal mass ejection, the photons are entering, and they are getting deflecting, and some of them, the ones that are not deflected, are entering the south and the north pole. So Earth's magnetosphere, or the shield that is there, it's doing a great job in protecting us from the most hazardous effects. So this is also an interesting graphic that I found. Okay, oops, sorry. Yeah. So the orange lines that you see, these are solar wind, and they are charged. And the red ones that you see here, the red lines near the Earth, are our magnetosphere, our magnetic field, our shield. And you can see that when these lines are coming, they were initially coming straight, but they got deflected because of the magnetic field. But some of them, if you look at this particular line, some of them got inside the Earth's atmosphere, and that's what caused the aurora. So, incoming particles are interacting with the atoms and molecules, and they become excited and they produce beautiful colors. So now we have an understanding that why this is happening. It's a beautiful phenomenon, but it is also something that we monitor very closely to make sure that it's not at a very high intense rate. So the colors that you see, and I'll show you one more interesting picture after we understand these colors. So when the solar wind is, this is basically the same graphics explaining the same thing, that the photons were coming perpendicularly, they got deflected, some of them entered our atmosphere, and then we got some colors. Now, as we get some colors, what we see here, that at about 150 miles above in the atmosphere, you see red color, which is not something that we usually see. So excited atomic oxygen at high altitudes is only visible under intense solar activity due to low concentration of oxygen. So when there's a low concentration of oxygen is when we see red color. Now, if we go up to 150 and we see the green color, that's because it's the oxygen at lower altitudes and it emits green color when it interacts with these photons. And then furthermore, when you are at above 60 miles, around 60 miles, you see these beautiful blue, purple, lilac kind of color, and that's because it is interacted with ionized molecular nitrogen. So that's why these different colors come, because of interaction of these photons with different gases that are present in our atmosphere at different levels. So this one photo I came across just yesterday, and so this is a beautiful place in New Jersey where I'm presently at, and this is actually a sea beach, and this is very south of New Jersey. So I'm still a bit north, but it is still very south of New Jersey. And what's interesting is that I'll show one more. Yeah, this one. So if you will look at this graphic, what you see is this is where the aurora is, and this is where I am, somewhere here, and we are still able to see the aurora. And this I'm talking is even southern of New Jersey. So where I am, people are able to see it after midnight. They are able to see beautiful colors. But what we see here is that the geomagnetic storm right now is so intense that even the places that are so below in the latitude from the North Pole are able to see this phenomenon, which is not a very usual thing to happen, but this has been happening since last year. So far, what our understanding has been is that there's our dynamic star sun. It is ejecting some coronal mass, and we have this whole communication system set up out there. Um, and we have satellites, we have our aviation system, we have our space programs where astronauts and the space stations are there. And everything that's on the ground is like completely connected with everything that's up there. And they all are so very well connected that if these solar activities affect any of this thing, it's going to cause a havoc. So there are actually some examples recently that happened. Not a few of them recent, but a couple of them that are pretty old. So the first one was actually in 1859, that there was a the storm was so intense that it actually produced access current near the telegraph lines. So though we don't have telegraph lines anymore, it can still affect our communication system. Then the previous one in March 1989, it was also a G4 storm, and there was a blackout in Quebec because there was a power outage, and it affected about 6 to 9 million people, somewhere between that number. And the more, if we see in the early 2000s, in 2003, a solar storm actually disrupted about 30 satellites, and there was a power outage in Sweden. So these things are actually happening. They probably are not happening very close in years, which is very, very good. But we are monitoring them very closely because we want to keep our satellites and our communication systems safe from any solar activity. Yes, so the very recent one is the one in February 2022 when the geometric magnetic storm destroyed up to 40 Starlink satellites worth $50 million. So that's a huge loss. And if we keep incurring these losses, it's only going to affect our global economy. So what are we doing to, keep all these things in check? We will come to that in a bit. And yes, these solar activities are dangerous for astronauts as well who work outside the International Space Station. Whenever there is a solar storm or something, they do not come out. They go in, they seek a hide or something inside the station, and they do not go for any spacewalks either. So in a way, the this particular graphic explains us that how everything is so interconnected, because any solar activity which is so intense is going to harm any part of it, including the aviation, because there are satellite communications that are happening while you are flying on board. So if anything goes wrong, you have a total sort of, complete disconnection from the rest of the world. So, all right. So, this has been our understanding so far that the space weather is impacting human space exploration, satellites, communication, aviation, electric power, because there have been incidents in the past. And of course, the aurora, the northern lights that we see, is also one of the phenomenon that is because of the solar activity. So, right now, we are in the solar cycle, the 25th solar cycle, and it's actually going to get more intense next year. It is expected that it's going to be the geomagnetic storms and all are going to be maximum, and the solar cycle is expected to be of about 11 years, and we see a lot of activities during this time: sunspots, solar flares, coronal mass ejections. And we also at points see that these activities are very less frequent. So it's an ongoing process, and one solar cycle is of 11-year in period. Okay, so understanding what are our current challenges. When we talk about our current challenges, of course, we need a prediction accuracy that something is going to happen, but we cannot predict that accurately. But if we still know ahead of time that there is a continuous solar activity going on, and if we keep monitoring it, we will probably able to be more prepared. The preparedness on the ground will be better if we know that there is something that may or may not hit us. So whatever the monitoring gaps are still there, we are trying to fill those gaps by sending missions out there that are continuously watching the sun and understanding sun better, understanding its dynamics in a better way, and keeping a close eye of regular, frequent or less frequent activities, especially right now when there is so much going on. And of course, there are some economic challenges as well, because it costs millions and billions of dollars to send things, to maintain them, to keep an eye on them. But this is something which is important. Like, we cannot skip it. So, what mitigation strategies we have? So, rather than strategies, I would say like these are things that are already in place. So, we have a monitoring and forecasting system in place. We also are trying to make our communication system and satellites better, satellite hardening, power grid management, and of course, public awareness and preparedness on ground. Like now, we are more aware about space weather than we were 50 years ago or 100 years ago. Like today, we are talking about it. So this is the kind of system that we have in place. This is a very beautiful graphic that I found from NASA. It's actually a heliophysics system observatory. So they call it observatory because it comprises of so many, missions that are already flying in there, solar probe, SOHO, that are closely watching the sun, monitoring it, taking its pictures on a regular daily basis, and making sure if there is something huge coming our way. Of course, we cannot move away from sun, or we cannot deviated, like we do in case of asteroids, that we have dart and other things in the space to protect us from something coming towards us. This is not something that we can protect us from. Like, we cannot put something to deviate those photons coming or the mass coming, but we can be better prepared. The preparedness will be better if we know that there's something coming. And of course, we also sent our mission from India, Aditya L1 mission, which is also continuously monitoring and watching um, our sun. It is in the L1 point, and I know that there have been like so much discussion on it, that's why I'm not going a lot into deep of this. But yeah, some of the time we can talk about it. And before we finish today, something that is very important is that our climate change that is happening, the increasing levels of greenhouse emissions, there are so many protocols that are in place, but still space technology plays a very, very important role in understanding climate change, because all the data that we are getting from space, all the images that we get from space, from our satellites of our Earth, uh, are helping us understand our planet better, are helping us understand that how and where we need to take certain steps to mitigate these issues, especially when it comes to rising temperatures, greenhouse gas emissions. And all this monitoring is being done from up there, because we are getting a whole comprehensive holistic, like a drone image from up there. And that's why space technology plays a very important role in climate change. And like I said in the beginning, that it is all like a circle, it's all very much connected. Because if there is any harm to our space technology because of bad space weather, it is going to implicate on our climate change. Because in the last 20 years or so, 20, 30 years, we have really worked on placing satellites there and get satellite imagery to understand the planet and the changes in the environment with the help of the technology. So, yeah, that's all for now. Thank you so much. Um, Please let me know if you have any questions.
Thank you, Megha. Thank you for such a wonderful presentation, and also the way you explained with the detailed facts and with the smallest detail to start with, like a space weather and a climate differentiation. I think it has helped people who are not from the astronomy background as well to get the detailed understanding about the topic we are discussing today. So, now we can like take some questions if you
Yeah.
have any doubt related to the topic we have discussed, the space weather, or you have something to uh,
Yeah, I
like
think
comment on.
yes. So till the time, if anyone has any question, you can actually read and study in detail about auroras. So auroras are also of, like, two types: what we see here in North Pole and what we see in South Pole. So you must have come across the terms like aurora borealis and aurora australis. So australis is more like, which is in the southern hemisphere. South pole towards Australia is where we see, and the borealis is in the northern hemisphere or the North Pole. I would actually say that this is something which is happening in the northern hemisphere now than the North Pole, because there used to be a time when people used to fly towards the places near the North Pole, at higher latitudes. But it is interesting that now, at such latitude where I'm able to I haven't seen it yet, but hopefully, but people are able to see where I'm living right now. So this is interesting phenomenon. And sometimes, like, we probably feel that, oh wow, this is something amazing, this is so beautiful, but it is important to understand that this beautiful phenomenon is nothing but a scientific phenomenon, and also it may cause certain harm also to us, which probably we didn't know before, uh, like in earlier days. Also, I would like to add that other than Earth, I think Jupiter also has auroras. If I'm not wrong, I read it somewhere. Yes, Jupiter has auroras too. So there are other planets as well that have very strong magnetic field like Jupiter, and they also experience auroras. So there's like tons of studies and pictures and videos that one can go through and learn more about auroras. Or we can do a special talk on auroras.
Definitely, we look forward for that, and hopefully, I think we
Yeah.
get chance to cover that. Like you can get a capture on your camera, so it would
Yes.
be very interesting to know more details in the coming lecture as well. So I think we'll wrap today's session. Although it is like we are open for the questions, but I cannot
Yeah.
see any questions coming in the chat
Mhm.
box.
Yeah.
So
You
we
can
can
leave
wrap.
an email to the
Yes, yes.
planetarium or in the chat box, and I will be happy to get back.
Yes, because this video will be available on Planetarium YouTube. So if you have anything related to the topic we have discussed today, feel free to write your questions. So we'll be happy to answer that.
Right.
Thank you once again, Mega. Although your presentation needs no further inputs to because it's so well prepared and well interacted with all the detailed facts related to the topic. But still, if you find any questions related to the topic, we'll be happy to share with you. Thank you once again for agreeing and being part of this learning initiative by Nehru Planetarium on World Space Week 2024. So we look forward for another opportunity, online opportunity with you in the coming time. Thank you once again.